Second speaker of the morning is Alessandro Sisto from Heriot-Watt, and he'll be telling us about drilling hyperbolic groups.
All right, thank you very much. Great to be here. So yeah, we have many co-authors on this project. So Daniel Gross, Peter Siski, Jason Manning, Damian Ozaida, who's here, should be here, and Genevieve Walsh. And the general problem we address, I hope it's, I hope you consider it a natural one. I would consider it a natural one, is understanding hyperbolic groups whose boundary is a sphere. Okay, so hyperbolic groups with okay, so what do we know? So let's start with very low dimension, dimension 0. So if we have a hyperbolic group, G, and the boundary is S0, so that is to say it's 2 points, then we know that G is virtually Z. And I guess this was known already to Gromov. Okay, maybe this is hopefully something that you've seen already. And so for the purposes of generalizing this, you should think of Z as the fundamental group of a closed hyperbolic one-manifold. Okay. Sorry that you don't believe in hyperbolic one-manifolds. And so with that point of view, when we pass to S1, there's an obvious conjecture, which is that G is going to be virtually the fundamental group of a closed surface. And this is indeed correct. So G is virtually phi1 of a closed hyperbolic surface. And this is much harder, though. This is already a lot harder, and actually the resolution of this is also part of the geometrization theorem for three manifolds in the cipher case. And so the names that contributed to this are Tukia, Casson, Jungreis, and Gabay. Okay. So I'm not going to go into who did what, but yeah, just it's a much more complicated result. And then there's a result kind of different. This is low dimension. There's a different flavor result for high dimension. I mean, different flavor of techniques, but same flavor of result, actually, I should say. So when the boundary is a sphere of dimension at least, was it 5? Yes, 5. And let me add the G is torsion free, so I have to add the G is torsion free. Well, I don't know if I have to. The known result is for G torsion free. Then we can no longer expect G to be the fundamental group of a closed hyperbolic manifold, because, for instance, there are negatively curved manifolds that are not hyperbolic in high dimension. But still, we can conclude that G is the fundamental group of a closed spherical manifold. Of the correct dimension, which is m plus 1. Okay. And this should be, this is a theorem of Bartels, Luke, and Weinberger. Okay. So just to address maybe natural questions, so it's a question in their paper: what happens when you drop torsion free? Whether you you can have G acts on a contractible manifold. They say that they expect that n equals n at least 4 should work more or less with the same techniques. I don't know if since the paper came out this has actually been done. I'm definitely not an expert in the kind of mathematics that goes into here. And there's a gap between here and here. And since I like three manifolds, what I really wanted to be in life was a three manifold topologist. I failed to do that. So the case of S2 is the one that's that has a lot to do with three manifolds, and that's the one that we're going to talk about for the rest of the talk. So what about S2? And there's a famous conjecture here, so Cannon conjecture. Which I will abbreviate CC because I will use it a lot. It says the following. So if G is hyperbolic and the boundary of G is S2, then G is virtually the fundamental group of a hyperbolic three manifold. So it's virtually by one closed. Okay. Which actually originally I think this was meant as a step in the proof of the geometrization theorem for three manifolds, which now we know is through further reasons, but I think this remains a very interesting question. Okay. So I will not prove this conjecture in this talk, but we have an approach. It'd be great if it worked out. Even if it doesn't, I hope that the things we develop are of interest anyway, so are of independent interest. So this has to do with relatively hyperbolic groups and the relative version of this Cannon conjecture. Maybe before I get there, let me make a small aside. And spheres are not the only possible interesting boundaries of hyperbolic groups. So I wanted to mention two results on other types of boundaries and that are somewhat related to this, and it's results of Kapovich and Kleiner for the one-dimensional boundary. So one of the things that they show is that if you have a hyperbolic group which has a one-dimensional boundary, the group doesn't split over virtually cyclic groups, then there's only three possibilities for the boundary. So the three possibilities are S1 that we discussed already, Sierpinski carpet, and the Menger curve. So the Menger curve is kind of the generic case. There's no kind of classification possible, probably. So for the Sierpinski carpet, though instead there's a result that I would actually like to write down because it's in a similar spirit to the results that I will discuss later. So Kapovich and Kleiner prove the following. So if you have G, which is torsion-free, hyperbolic, and the boundary is a Sierpinski carpet, okay, so and Cannon conjecture holds. So then there's then G is the fundamental group. So it's again a hyperbolic manifold. It's no longer closed. It has boundary. It's a compact hyperbolic three manifold. And the peripheral circles of the boundary of the Sierpinski carpet correspond to totally geodesic boundary components. So closed compact hyperbolic three manifolds with totally geodesic boundary. So if you want, there's a Sierpinski carpet version of Cannon's conjecture, which is implied by Cannon's conjecture. Okay. Very good. So now I'd like to discuss relatively hyperbolic groups. I would actually like to give a definition. I expect that maybe most of you know already one of the definitions. There's one particular one that is useful for this talk, and it's the one with the version with the cusp space. I guess originally due to Bodic. So okay, let's. Yeah, this is not. Well, okay, let's start here. So relatively hyperbolic groups. So before giving the definition, I have to give you only one construction, which is the construction of the combinatorial horrible, which is the following. So it's like a machine to start with a graph and make it hyperbolic. So you take your favorite connected graph, with the standard metric, like every edge is length 1. So it could be a Cayley graph. You should think of it as a Cayley graph, in fact. And then out of this, we construct the combinatorial horrible. H of gamma, which is something that simulates the metric of a horrible in hyperbolic space, in the kind of real hyperbolic space, in a combinatorial way. So so this is a graph, or a metric graph. I have to give you vertices, edges, and lengths of edges. So the vertices are just something boring is just gamma 0 cross n. So just the vertices of gamma and then times n. You should think of it as kind of layers of copies of gamma. So there's a base copy of gamma here, and then other stuff. So the edges, I'm not going to write them down formally. It's just the obvious horizontal and vertical edges. So horizontal and vertical edges. So the horizontal edges are the ones that come from gamma, and the vertical edges they connect copies of gamma in different layers. So there are these vertical rays. Okay. So, and then I'm gonna not give it just the graph metric because that's definitely not hyperbolic. I'm gonna let me just draw it. So metric, as in the picture. So the vertical edges have length 1. Okay, so all these have length 1. But instead, the horizontal edges at level n have length 2 to the minus n. Okay, so they shrink as you go up. Okay. And the exercise is that h of gamma is hyperbolic. With a very low constant, I never sat down to figure out the optimal constant. 10 is definitely enough. Okay. So, and this is not so hard. Like, you have to understand what geodesics look like, and if you think about it for 10 minutes, you will realize that all geodesics look like this. So they go straight up, across a bounded amount, and then down. Right. So they cannot zigzag because doing this is longer than doing that. that's the key observation is just up, like which way do you go around the square? Okay. So very good. And then now the definition. So a group G is hyperbolic relative to a subgroup. So there's versions where they're not required to be finitely generated, but let me just have them both finitely generated. If a certain space that I will denote X, G, H, so often called the cusp space, is hyperbolic. So how do I construct this this space? I start with a Cayley graph, with a Cayley graph. For G, let me take a generating set which generates also the peripheral subgroup. So this is called the peripheral subgroup. Okay, so this thing is in general not hyperbolic. But the idea is that I want some group whose non-hyperbolicity is confined into a given subgroup. And how do I say that? Well, I say when I turn that subgroup into something hyperbolic, I get something hyperbolic. So I do that by gluing in copies of the combinatorial horrible over, well, let me do it like this, slightly informally. So overall copies of the subgroup. So the picture, which probably if I draw here you cannot see, so I'm going to go somewhere else. So the picture to keep in mind is you have G, or the Cayley graph of G. It contains all the various cosets of H, and I'm attaching like this thing that I'm thinking of as a cusp over all the cosets, and on recurring, then what I get is hyperbolic. Okay. And this framework fits, so not quite close hyperbolic manifolds, but finite volume hyperbolic manifolds. So, for example, we got.
You might want to finish the definition.
Oh, sorry. Yes, thank you. I tend to forget to write is hyperbolic at the end of this. So is hyperbolic. Okay. So, and this is meant to capture fundamental groups of finite volume hyperbolic manifolds, which look like this. So finite, yeah. So such a manifold has like a compact part which carries the fundamental group, and then some product regions that go to infinity, which you should think of as a product of like a torus times 0 infinity. And yes, so this is the fundamental group of this is the peripheral subgroup. Okay, so I should say that you can do it. I mean, such a manifold can have more than one end, like this, and indeed, relatively hyperbolic groups can be hyperbolic relative to various subgroups. I just decided to stick with one, just for simplicity of notation. There's nothing else tricky in adding more peripherals. Okay, so and there's plenty of these. These, for example, so sub-example, there are lots of knot complements that are like this. So S3 minus the figure 8 knot complement. That's such a manifold. And the neighborhood of the knot is this cusp. Okay. So, and that's the most relevant example for what we're gonna think about, like finite volume hyperbolic manifolds. Any questions? So I want to talk about boundaries. So if I write a single line here, can everybody see? Yeah. Okay. So just like hyperbolic groups, relatively hyperbolic groups also have a boundary, and it is the boundary of this of the cusp space, of this space. So definition. So I'm gonna be sloppy with notation. It's really a given relatively hyperbolic group has many different relatively hyperbolic structures. So I should really write the boundary of G with respect to a given subgroup. I'm not gonna do that. Okay, so we'll just write the boundary of G. So that's just the boundary of XGH. Okay, I don't think this will cause confusion. Okay, so with all this in mind, very nice. So I still have Cannon's conjecture here. So let me state a different version of Cannon's conjecture, which I want to call relative Cannon conjecture. Okay, and this is in Kapovich problem list on boundaries of Kleinian groups. Yeah, I don't know. I think that's the first time it appears in writing them. So you can, given what I wrote on the board, you can kind of guess probably what the conjecture is going to state. So if you have G, which is no longer hyperbolic, but now it's hyperbolic relative to Z squared. Okay, so relative to some subgroup which is isomorphic to Z squared. And the boundary is S2, right? So this space that I described here, XGH, if you do that construction for these fundamental groups, you get something that's basically hyperbolic 3 space, something quasi-symmetric to it, and so the boundary will be S2. And that's the conjecture is that that's the only groups that have this type of boundary. The only relatively hyperbolic groups that have this type of boundary. So G is, in fact, for I can even drop the virtually. So there's a virtually here. Let me put it in parentheses. You can tweak the conjecture, like, instead of Z square, have like virtual Z square, and then you need the virtually anyway. So G is the fundamental group of a finite volume hyperbolic one. Okay. Very good. So that's natural conjecture to make. It's also related to classification of Poincare duality groups. No, I'm going to talk about that. Okay, and now I'm going to start talking about my own results in the area. So there's a result from now several years ago with Daniel and Jason. So that this was kind of let's say inspiration for then this work. So I'd like to talk about this one also. So with Groves and Manning. So what we proved is something in the style of Kapovich and Kleiner. Like, if Cannon conjecture holds, then some other version holds. So Cannon conjecture implies relative Cannon conjecture. And so how do we do that? So telling you how we do that will be an excuse to talk about filling of manifolds, which, I mean, in that paper instead we reverse the process. So to do this, we prove the following. So we start with the setup of relative Cannon conjecture. G is hyperbolic relative to z squared. The boundary is S2. Okay. And from this, so what do we do? So there is this classical procedure that Thurston used a lot, which is to starting with a hyperbolic manifold of finite volume. So you can chop off the cusp. So it doesn't carry any fundamental group, so why not? And now you have a manifold with a torus boundary. Now you like closed manifolds more than manifolds with boundaries. So how do you make a closed manifold out of that? You can plug in a solid torus in here. So a solid torus is D2 times S1, and you can glue it in various ways. So you have to decide where to map the meridian. And so Thurston showed that for kind of a generic way to put a solid torus in here, you get a hyperbolic manifold. And at the level of fundamental groups, what happens is that you start with your fundamental group G, and then you're killing that's the meridian. So you're killing the element of the fundamental group that corresponds to the meridian. So the fundamental group of the field manifold looks like this. So it's G mod by the normal closure of some element H in the this H. So relative in the subgroup. And okay, you have to avoid finitely many elements. So let me just be sloppy and write generic. Okay, so this thing due to work of Hausen and also Gross Manning is known to be relatively hyperbolic. It's known to be a hyperbolic group in this case. And so this group is hyperbolic. I can take the boundary. Okay, let me be a bit more precise. So G bar, this is hyperbolic. Okay, this is not our theorem, Hausen and Gross Manning. And the new thing is that the boundary is S2. Well, the new thing at the time, by now this paper is it's not that new anymore. Okay. And yeah, so this is, we have kind of a general procedure to try to understand boundaries of the infillings, which I don't think I'll have time to discuss. Hopefully I'll say a few words at the end, and if not, please do ask me after. What goes in here. So, okay, so once you know this, from Cannon's conjecture, you would then deduce that G bar is virtually a three-manifold group and a hyperbolic three-manifold group. And basically, you can extract, so forget about the virtually, you can extract a sequence of representations. G to the isometry group of H3 which factor through these type of G bars. So G bar really depends on H, so you vary H. And then you make these converge, and that's how you prove that. So once you know this, how you prove that canon implies relative canon. It's not. I mean, it's not that hard once you know a few things about representations.
Alex, so you think you don't appeal to geometrization in that argument at all? You're not arguing that. You're not arguing that G is a three-manifold group and then concluding it's hyperbolic by some sort of geometrization. You're actually constructing that.
Yeah. Yeah, that's right. Okay, so this is great. So Canon conjecture implies yet another thing, so we should really prove Canon's conjecture. However, now I'm gonna try to convince you that that's the wrong theorem to prove. Okay, so the paper is published now, so it's fine. I can tell you that was the wrong theorem to prove, because relative canon should be easier than canon. Okay. I want to spend some time trying to convince you of this. Let's skip to here. So why do I think this should be the case? So the reason is a parallel with the geometrization theorem, or the hyperbolization of three manifolds. So the reason parallel with hyperbolization which Misha Kapovich wrote a book about, and yeah, you can read everything about it there. So roughly what's the statement of that? So the theorem, in quotes because I'm not going to be precise, is that if you have some three manifold which is compact but might have boundary and has certain topological properties, okay, so that don't matter at all for us, it's just a parallel, then M is hyperbolic. Or rather, to be precise, the interior of M. Because remember, this might have a torus boundary, right? So maybe I have to remove the torus to see the cusp. Okay, so the interior of M is hyperbolic. Okay, so this, so an important case of this was proven by Thurston in the 80s, I guess, 70s, 80s, and so he could prove the case that M is Haken, which is another topological property. The only maybe thing to keep in mind if you're not familiar is that Haken manifold contains a pi1 injective surface. Okay, so and then it was only work of Perelman using Ricci flow that then was able to deal with the general case. Possibly a manifold that doesn't contain any surfaces, any nice surfaces. Okay, so already from here, maybe you see, okay, there's more chances of kind of being in, like, not copying, but like following the steps of Thurston than work of Perelman, and so why is this thing relevant to relative versus absolute canon conjecture? The point is that if the boundary is non-empty, then M is Haken. Okay, so hyperbolization is easier. It's still very hard, but it's easier when the boundary is non-empty, which corresponds to to the relative case, to having actually a peripheral sum. So let me say a bit more actually about this. Okay. So what can you do here that you cannot do in general? So the key for Haken, for the Haken case, is that since you have this this surface, you can use it to cut the manifold. So you can use surface sigma cut, okay, to cut M. And so in particular, since this surface is pi1 injective, you will get a splitting of the fundamental group. So that's one thing you get. And yeah, and maybe more precisely, like these certain topological properties that I didn't tell you about persist under cutting. Okay, so same. Okay, so it's really important to do this theory. So even if you're only interested in closed three manifolds, it's important to develop the theory also for manifolds with boundary for this reason. Okay, so yeah, you get a manifold with boundary, but it has the same topological properties. In particular, it has again a surface that you can keep cutting, and you can cut again, and so you can do induction. And this kind of hierarchy of cutting has to stop at some point, so you can do inductive arguments. Okay. So what's the dream? So now, why can we maybe be inspired by this and go out and prove relative canonical conjecture? So here's the plan/dream. So right. So we start with our hyperbolic groups. Sorry, non-hyperbolic groups, but it's hyperbolic relative to z squared. And the boundary is S2. So the first thing is that G should have some kind of splitting. So just like here, so split G. And that's kind of the only part of the plan that there's some evidence for. So right, kind of, we know how to compute the boundary. Sorry, how to compute the homology and cohomology using the boundary. So that's kind of for hyperbolic groups. This is work of Vespin and Mess, and then it's been developed further. And in particular, in this case, you can conclude that H1G is non-trivial. So if you have a manifold with boundary, so you know that half of its homology survives. So half the homology of the boundary survives in the homology of the manifold. And there's something similar. Okay, so split G. And then you have to understand the factors. So we don't know that there's a nice kind of I1 of a surface inside one of these G's that you can use to catalog. So that would be the first thing to understand if you actually have something like that. And then somehow induct. So hyperbolize. Okay, so right. So we can't do. So honestly, I haven't thought much about this further parts of the plan. Some of my co-authors have. But yeah, so far we don't have anything in that direction. But at least, you know, the first step that we do have with a little asterisk. So let me tell you what the theorem is. I'll write it here. Theorem. So relative canon implies canon for residually finite hyperbolic groups. So that is to say, if you have a hyperbolic group, the boundary is a sphere, and you know it's residually finite, then it will be virtually one of a three manifold. So yeah, if you believe that all hyperbolic groups are residually finite, you can drop that. But Sam is not convinced. But the ones with S2 boundary, so if canon conjecture is true, you know, any hyperbolic groups with S2 boundary is residually finite. Okay. So what is it that we prove to do this? So we prove. And we kind of reverse the. Yeah, I shouldn't have erased the previous theorem. So let me just write the upshot of it. So the boundary of G of H is S2. So this was the kind of the key formula in the previous theorem on the other implication. Canon implies relative canon. So what we prove is the following. So we start with G hyperbolic. The boundary is S2, and G is residually finite. And then we make a relatively hyperbolic group. Let me call it G drill. So hyperbolic relative Z square. Okay. So this has boundary S2. And so there exists this, and we have to pass a finite index subgroup. So G, let me call it G dot. finite index in G. So such that G dot is a filling, so kind of a group theoretic filling of G drill. Such that G dot is G drill mod the normal closure of some element in Z square. Okay, so I guess okay. So right, it looks a bit complicated. Let me draw the manifold picture. What you should have in mind for this, and then you can turn the picture into the statement. So here's what you should be thinking. So think that so that G is the fundamental group of some 3-manifold M. So right here. Okay, so here is M, and then you pick your favorite element of pi 1, so your favorite curve. So this gamma. Okay, so and then you have a knot, let's say, so a curve. Okay, and then what is this G drill supposed to mimic? Well, it's supposed to mimic what you get by removing gamma from M. So, but let's maybe for psychological reasons, rather than removing just gamma, let's remove a neighborhood of gamma. Okay, so this thing here is a neighborhood of gamma. And then, yes, so you would like G drill to be the pi 1 of M minus the neighborhood. Okay, so it has a torus inside, so it makes sense that it's there's a Z square inside. And what is this element of pi 1? It's the meridian. So H is the meridian. Okay, so how do I get back the fundamental group of M from the fundamental group of N minus gamma? By removing N of gamma, I created an homotopic loop, and I have to fill it back in. Okay. So, and drilling 3-manifold is also a very well-known procedure that obviously we're not the first to think about that, and and that's what inspired this thing. Okay. So right, and then if you know relative canon, you know that this thing is the fundamental group of a 3-manifold with boundary, and then this will also be the fundamental group of a 3-manifold. So for this one, we actually do use geometrization instead. We don't bypass geometrization. It might be possible to bypass geometrization if you understand better this meridian, but we don't know how to do that. I mean, to use instead Thurston's filling theorem instead of geometrization. Okay. So, right. So this is very manifold. So how are we gonna do this group theoretically? So let me re-describe this in a more complicated way. That's, however, then generalized. I mean, that you can then turn into a group theoretic construction, or like geometric group theoretic construction. So for
G, I mean, G has torsion.
Yeah, so actually, let me think. So maybe in the proof of this, we first pass to a finite index subgroup with our torsion.
And then G dot works drill one should also be quotient.
Yes, the drill one is, yes. So I didn't write everything that we know about the, yeah. You're right. Okay, so how do we reinterpret this this picture? So it's better to think about the universal cover of M, first of all, because the universal cover is the thing that looks like the fundamental group. So let's say different perspective. So we're gonna look at the universal cover, M tilde. So I'm thinking of M actually as a hyperbolic manifold. So I'm drawing the Poincare model. And okay, and then there's this gamma that has various lifts or elevations. So this is some of the lifts of gamma tilde look like that. Okay. And this neighborhood lifts to things. I mean, if this is again a hyperbolic manifold, the lifts of the neighborhoods look like bananas. So like. Okay. So these are lifts of the neighborhoods. And how do I reinterpret the drill group in this case? So G drill. Okay, I could do it in one step, but let me do it in two steps. So we're gonna start with M tilde. So instead of removing just one neighborhood, we have to remove the union of all the lifts of the neighborhoods. So M tilde minus the union of the bananas. So this is a cover of of M minus N gamma, but it's not the universal cover. We have to pass to a further cover. Okay, so this thing here is the universal cover of N minus N gamma, and then the fundamental group is the DAX group of the universal cover. So okay, and when you think about it in this way, that's the way that you can make to work in more generality. So let me just write it. So this works whenever you're in a situation where you have G dot some group, which is going to be no longer G but a finite index subgroup. So it acts geometrically on some hyperbolic space. Okay, and so to make things work in the coarse setting, what you need is that all these transits of the axis are very, very far apart. Okay, so definitely much further apart than the hyperbolic C constant, for instance. Okay, there's also other parameters though. Okay, so translates of axes of gamma are very far apart. Okay, so I'm writing it like this because it's not going to be G dot acting on its own Kelly graph. It's going to be G dot acting on the Kelly graph of G. Right, so you pass to finite index subgroups, keeping the hyperbolic C constant the same, but you can ensure that axes are sufficiently far apart. And okay, I only have 3 minutes. So if this was a hyperbolic manifold, why would this thing be relatively hyperbolic, roughly speaking? Or at least what's the idea? So this cover here, it looks like, so locally it either looks like the universal cover of M tilde. So if M is hyperbolic, that means it's negatively curved. So there's some neighborhoods which are just negatively curved. And then close to the boundary here, instead, okay, it's no longer negatively curved, but there's just kind of the flats that you obtain from unwrapping the boundary of the neighborhood. Okay, so the boundary of the neighborhood is this cylinder. When you pass through the cover, the cylinder gets unwrapped to a plane. But those are the only planes. Okay, so this is why you should believe that that this is relatively hyperbolic. And to do this type of things in the course setting, what you use is Cartana-Damart for hyperbolic groups. So there is a local to global statement which says that if you have a space where sufficiently large balls are hyperbolic, then the space is hyperbolic, okay, with some lies. And that's right. And basically having the tubes very far apart is what allows you to say that, okay, in any of the balls that I have to check hyperbolicity in, I can only see at most one tube, which helps a lot with groups. Okay, and that's all I have time for, so thank you very much. Question?
Yeah, just a historical comment. When you were talking about the dream there, it's reminiscent of what Misha and I were discussing back in that time frame. So we started with the paper about hyperbolic groups with one-dimensional boundary, and then started thinking about the Sierpinski carpet case, and so then that led to kind of exactly this dream that you're talking about. That you've got a PD3 pair, and then you can try to show that PD3 pairs actually are homotopy equivalent to free manifold pairs by using this kind of hierarchy or inductive hierarchy argument. And so we wrote a follow-up paper. So it seems like the only missing piece is basically producing a surface subgroup or PD2 pair subgroup. And then, you know, the inspiration was this Scott-Shalin compact Core theorem that says if you have this splitting, you can find a surface subgroup in the case of a three manifold. And so we tried to imitate that in this setting of PD3 pairs. And the follow-up paper where you can produce a surface subgroup, provided you can get a subgroup that's FP2. So it seemed like there was just a small missing piece. So.
Thanks, I should have mentioned that. There is something in that direction.
Yeah, so I mean, what you're telling us is, I mean, you cannot drill every closed curve in a hyperbolic sphere manifold. What you're telling us is you can find, from the pure group theoretic point of view, a curve which you can drill. So, right? Can you maybe translate this into more hyperbolic geometry situation or language?
Actually, so you can pick any curve, any element G, and then find a suitable finite index subgroup for that. And actually, and also in the context of three manifolds, you can drill any curve, any simple curve.
But it's not clear whether you get a hyperbolic manifold that way. I mean,
So sorry, what did you?
I mean, it's not clear that you cannot drill absolutely every curve from a hyperbolic three manifold and just get a hyperbolic manifold with geometry finite or this finite volume.
I thought so, but actually it's true. I also thought that not all curves would work, but turns out they do. Or like, I mean, you use using topology, though, like, you know, that meaning that you don't construct the metric explicitly.
No, of course. I mean, you can never construct a metric explicitly, right? Okay.
Yeah, but I mean, it's not like you deform the metric. Like, you know, you check topological properties. And it works.
one more quick question.
No.
So, okay, so you just take this arbitrary element of the hyperbolic group and you define this drilling. It only depends on the element, right?
Yeah, you can.
So, do you have any idea how the presentation of this looks like?
Yeah, it would be nice to write that presentation, but and we thought about it.
The presentation of the drilling, the G drill.
So, let's say we don't have an explicit enough presentation to work with. Principle you can, but there's gonna be like huge relations for the.
Oh, it's not only one that. Okay.
No, not really. Yeah.
Just a question for the organizer. Do we know when the photo is? The photo at past or right now?
Yes.
Okay, so we're going to go outside for. Well, let's thank Alex again, and then we'll go outside.